solve it. And thought Peter would have that explain it to us. So I don't think it was like, but it was not live. I don't think it'll be live. So hopefully I'll be good.
All right, I know you like a couple of homework. I think the grader's gonna be behind. I'm gonna try to light a fire and maybe take back one. Anyway, I'll get you some stuff soon. If anybody's got any concerns, let me know. And I can, give you feedback before you get your homework back. Any other questions before we go? All right. So, how many of you have heard the terminology prime? Right, a number is prime. Right? You've almost always heard this in context of the integers, I suppose. How many of you have heard the terminology irreducible? A lot of times this is used synonymously in the integers. And actually, if you're thinking about non-zero elements, irreducible and prime do the same thing in the integers. They're not, this is not true in general. So let me start off with a definition here. And I want R to be community. Not unit. So I want this element to be not zero, and I don't want it to be a unit either. Is irreducible. Yeah. So what it needs to be irreducible, and actually you should think integral domains because you can find generalizations of irreducibles that are, in fact, think first of all in integral domains first. Irreducible means if you can break it down, pi is AB, so you can factor it down, then one of those factors has to be a unit, right? This is analogous to thinking in the integers. The old definition of prime that you may know is all its factors are itself in one, but actually plus or minus one, a unit. Now, if you allow zero divisors, there are actually three different definitions of irreducible that all collapse to this one. Irreducible, strongly irreducible, and the imaginative very strong irreducible. I'm not going to get into that right here. Now, the definition that is pretty constant here, non-zero, non-unit, is prime if E divides AB How many of you have seen both of these definitions used to describe prime integers? Right. Sometimes you'll see these used in tandem, and for non-zero elements in the integers, these two definitions are actually equivalent, but they are not in general. Sample. In Z, primes and irreducibles. Coincide. Technically by the definition here, actually, actually, for prime here, I think, even though I wrote it there, I'm gonna remove that. Because I can use this in more general setting. So in Z, the primes, the non-zero primes, and the irreducibles coincide. Zero, if you look at this definition, is technically prime because zero divides AB, right? Implies in the integers, zero divides A or zero divides B, because the only element that zero divides in the integers is zero, right? Because remember what it means for something to divide something. We went through this last time. And of course, the integers, if the product of two things are zero, one of them's got to be zero. This also brings up the why the term zero divisor is called zero. It's called zero divisor. It's called what it is. Because if you have A times B equal to zero, that means that that means that zero divides the product of those two. Let me give you a more fun example. This is one of my favorite rings for examples. Take your favorite field. So this is a field. And look at this right here. This is almost a polynomial ring. So what does stuff look like here? Notice if you have x squared and x cubed, you've got x to the fourth power, right? Multiplying that by itself. You've got x to the fifth power, multiplying these two. You've got x to the sixth power, multiplying that twice. And now you've got every other power. The seventh power is this and two of these. The eighth power is two of these and this. There's many ways to do it. So basically what this ring is, if you will, these are just polynomials that are missing the linear term. That is to say the linear term has zero coefficient. Right. What happens if you add two polynomials that are missing the linear term? You can't magically, spontaneously get it out of nowhere, right? But what happens if you multiply two polynomials that are missing the linear term? You can't make a new linear term out of it. Do you agree with this? This is a ring, and in fact, it's an integral domain, right? Because it has no non-zero zero divisors. Notice that x squared is irreducible. And so I'm going to appeal to what you probably, I hope, already know a little bit about polynomials, although we'll talk about this a little bit later. If you could factor x squared down into smaller polynomials, you've only got two choices. The degree of x squared is 2, so you can factor it into a degree 2 and a degree 0. Do I agree with that? But that doesn't work because a degree 0 polynomial is a unit, because the ring here, the coefficients are a field, right? So if you have x squared, if you have alpha times alpha inverse x squared, alpha is a unit, right? So you don't want that. Your only other choice is to break x squared down into two linear polynomials. And cheater, pumpkin eater, no linears, right? So x squared is actually irreducible. If I agree with that? Same argument for x cubed, a little bit more complicated, but breaking x cubed down into a 0 degree and a 3 degree doesn't work because the 0 degree has to be a unit. So no matter how you cut the cake after that, you have to have a degree one factor to break it down, and I ain't got none. So everybody on board with these two are irreducible. Now, watch this. Nothing up my sleeve. Notice that x to the sixth factors these two ways. And in fact, this does not mimic the integers because you don't get unique factorization. In fact, not only that, not only does it factor these two ways, but the lengths are different. You have three irreducible factors here and only two here. And let me point out that x squared divides x cubed becomes x cubed. But x squared does not divide x cubed. So x squared divides the product of these two things without dividing either element of the product. So x squared is not prime. So here this example produces something that is irreducible, but in fact is not prime. Right? You're used to these being synonymous in ordinary integers. Here's an example that further stinks up the room. Consider C6. Now I've got 0, 5, 1, 0, 5. Weird things can happen. Notice that you can go through and check this definition, but one of the things that we will see in the next theorem, here's an easy way to check that 3 bar is prime. This will follow from the next result. If you look at the ideal generated by 3, you get 0 and 3 bar. This thing generates a prime ideal, and so the element itself is prime, and that's a result we will see in the next bit. But you can go through and check all possible products and see that if 3 divides the product of two things, it has to divide one of the two. Right? Because in fact, in this range, 3 only divides 0 and 3, but it's not irreducible. Notice the 3 bar is 3 bar times 3 bar. So here we have 3 bar is a product of two things, and neither of them is a unit. So here you have an example of an element that is prime but not irreducible. That effect can only happen when you have 0 divisors, as a matter of fact. And in fact, this is a terribly bad ring because if you want to talk about factorization, idempotent elements, that is things that square to themselves, mess up things very badly. Okay, any questions? Theorem. And in this theorem, these kind of results, including one about the ideal generator. The non-zero elements. I'll tell you where integral domain is. Only if the ideal generator of I'm gonna prove this one because I don't think this needs domain actually. I'll make a note of that. Is irreducible. If and only if is maximal among not among principal proper. I don't think you actually need domain for this too. You do need it for C though. P is prime. P that you do need domain for. D, if R is the PID, then P prime, if and only if P is irreducible, this only applies to non-zero primes. Every associate of a prime irreducible and F the only divisors of an irreducible pi are associates okay, so let's prove some of this stuff. In particular, let's do 1 and 2 at least. A. Suppose that P is prime. That will occur. Our burden is to show that this is prime ideal. Well, remember, in this situation, we have a community room of identity. To show that P is a prime ideal, we have to show that a product of two elements of P means that one of those two has to be in P. That means AB is PR. Therefore, P divides AB. So P divides A, that loss of generality. And so A is in the second. So there's one direction. Now let's suppose that P is a prime ideal. divides AB, well, we gotta show that P divides one of these two. So, AB equals PR for some R and R, which of course means AB is in the ideal generated by P. Because the product AB is multiple C, so it's in the ideal generated by P. So P is the prime ideal. So without loss of generality, A is in the ideal generated by P. So A is equal to S. Therefore, looks to me like we don't need domain there. In fact, I think we may all need C and number B. I want to do this so I can clarify what I mean by this statement here, maximal among principal ideals. This does not mean that the ideal generated by pi is maximal, like it's usually not. But it is maximal among the set of all principal ideals. That is to say that if you have any ideal properly, any proper ideal that you make, it cannot be principal. And I do mean proper because one ideal that will contain it will be the whole ring, which is generated by one. But any proper ideal that contains it can't be principal. So let's assume that actually let's do the contrapositive here. Suppose it's not maximal. So what does this mean? There's a principal ideal strictly contains R that contains, as pi is in this ideal, there exists R and R such that pi is R times a little funny tornado letter thing. So let me also note that R is not a unit, because if it was, R inverse pi is equal to this thing. And so this thing can't be a unit, because otherwise you get that this thing is contained in the ideal generated by pi. So you get equality here, which is contradiction. Therefore, pi is not irreducible, because we've shown that R is not a unit, and this can't be a unit, because otherwise this contains it. So there's one direction of B. Now we want to show the other. I'll do the contrapositive again. Do the contrapositive. Let's assume that pi is not irreducible. Then pi is AB with AB not R. So these are proper divisors, if you will. Therefore, it's easy to see that pi is strictly the same again as either one of these. And so not maximal among principal articles. And I'll let you sort out. Yeah. No, I want to do C and D. And I'll let you all sort out again. Let's do C. This was kind of important. P is prime implies P is irreducible. Let me remind you the hypothesis here is that P is a non-zero prime. Okay, so what I want to do is, I mean, I'm forced to show that either A or B is a unit, right? That's where I want to get on this. So P divides AB. Right? Therefore, P divides A without loss of plurality. So here's the structure so far. Suppose I can factor P into A times B. I need to prove that either A or B is a unit. Well, this certainly means that P divides AB. And therefore, since P is prime, it has to divide one of them. So we'll just pick A. So A is equal to PR. Well, let's go back to the original equation. I get P equals A, which is PR. Now, this is where we have to use integral domain, and you shouldn't be surprised by that because in the previous example, I gave an example of a prime that wasn't irreducible, but it wasn't, it had zero divisors. All right, but here I've got no zero divisors. Since R was a domain, P is not zero. That's important. Then I get 1 is RB. Therefore, P is a unit of R. And so P is irreducible. Of course, this proof is symmetric in the sense that if I had picked P to divide B without loss of generality, I would have gotten 1 equals RA and then A. And finally, if R is a PID, then P is prime if and only if P is irreducible. Okay. By the way, there's a more general statement here we'll see later. This is also true for R being a UFD, which is a little bit more general than a PID. But this should feel all warm and fuzzy with you because my favorite principal ideal domain, my favorite integral domain where every ideal principal is the integers, right? And remember, we've come full circle now because we said that if you have non-zero integers, then prime and irreducible are the same. So this gets this result we wanted. So let's go for this. As far as a PID, then P is a prime. So R is a PI domain. That's all we need here. And P is not zero. So P is irreducible. Let's see. So we've already essentially done that part of it. The other part is, the interesting part is, why does irreducible imply prime? I use B. Now, suppose is irreducible. Then by B, part B says that an irreducible element is one, so it's ideal, it's maximum among principal ideals. Do I agree with that? But guess what? All freaking ideals are principal. Because we never did. All ideals are principal, and so being maximum among principal ideals means it's maximum among all ideals. So pi is a maximum ideal. So prime. So that dealing with pi is prime. Part A. And of course, again, we've seen examples. Where you have elements that are irreducible but not prime. They can't be principal ideals over time. So let me throw this again. So see if you can check this for yourself. This is the example that we produced where we had elements that were irreducible but not prime. Look at the ideal generated by x squared and x cubed. Another way to look at this is, again, this is the ideal consisting of every element in that ring, such that when you plug in 0 for x, you get 0. Right? See if you can show that ideal is not principal. We use definition first on the one. The following definition. And this definition is really, this is kind of the heartbeat of wanting to talk about factorization here. Factorization in integral domains in particular. What do you suppose you talk about when you talk about factorization? When you take an element and you start factoring it, right? You want this process to end, do you not? Right? I mean, what if you could take something and you factor it and you keep factoring it and it just never ends, right? You want to eventually get down. I mean, if you take an integer like 30, right? You say, well, what's 30? Well, it's 6 times 5. Okay, and you start looking at that and you say, well, the 5's stuck, right? I can only put ones and minus ones out of the 5, right? So, okay, you're done with that. So 5, ding, ding, ding. It's irreducible. The 6, you say, well, I'm not done with you, 6, because I can pull you apart into 2 and the 3. When I do that, I'm stuck, right? You want that to happen in factorization. You want to be able to get down to a point where you can't factor it any further in a meaningful way. Definition. We say, well, actually, let me preface this by saying, you can extend this definition to domains that are, or to rings with zero divisors, but it's crap sandwich without bread. It's confusing, and we might go over it later. But for now, let R be an integral domain. Say is atomic. Yeah, every non-zero, non-unit, so everything from zero in units can be expressed as a product. So what it means to be an atomic domain is you can actually write everything. It's not zero, not a unit. I mean, you obviously never write a unit as a product irreducible. And if you're in an integral domain, if you write zero as a product of something, one of those things, the product has to be zero. So why is this called irreducible? Irreducibles in commutative algebra are sometimes called atoms. The idea there being irreducible to the things you can't break down any further. Now, please, nobody start making jokes about quarks and so forth. Somebody define this without reading their physics books very carefully, but we'll just go with it, okay? So, atomic means you can factor things into a product of atoms, irreducible. Now, here is a question. Okay, Z is atomic, right? In fact, Z has the fundamental theorem of arithmetic. I can write everything in product primes. How can I prove that? The Euclidean algorithm, for example. Because what you can do, you can use the Euclidean algorithm, take your favorite element. If it's irreducible, if you can't factor it, you're done. There it is. It's an irreducible. If you can break it down into smaller stuff, right? And the smaller stuff can only go so low, right? And that's essentially how that works. This is atomic. Polynomial ring over field in a one variable is atomic. Polynomial ring over field in variables is atomic. Polynomial ring over a field in uncountably many variables is atomic. Polynomial ring over Z and uncountably many variables is atomic. Anybody ever had a class with Gary? Well, does anybody know what a Noetherian ring is? The Noetherian ring is a ring for every ideal time generator. A lot of carriage research is in this kind of thing. Like you can do lots of computations there. Any Noetherian ring. And if you don't know what that is, it just means that all the ideals are finitely generated. Let me say domain just for clarity. Any Noetherian domain is atomic. And we'll talk about the theory rings later. So this does beg the question, doesn't it? I mean, I'm a total tool if I sit up here and have a totally vacuous definition, right? Is everything atomic? I'll give you two examples of rings that are not atomic. And in fact, in my second example, it'll be a ring that has no irreducibles at all. And it's not a field. Let me point out that a field is atomic vacuously. Because if you have a field, every non-zero non-unit can be expressed as private irreducibles because there are no non-zero non-units, right? So in a very silly way, a field is atomic. This is QX. This is polynomials over, and in fact, this has the fundamental theorem of arithmetic. You may not know this yet, but we're going to prove later that if you have any polynomial ring in a single variable over a field, it's a Euclidean domain, so it's got the fundamental theorem of arithmetic. That's not even atomic. Weird, huh? Let me explain what this is. These are ordinary polynomials with rational coefficients. One stipulation, and this one stipulation is totally killer. I demand that the constant term be an integer. Notice that this is a ring because if you have two polynomials, a constant term and integer, you've got a constant term and integer. The product of these things is still got constant term and integer. But there are elements in here you can't factor into irreducibles. Anybody see one? This is such a slimy thread. Not a top. Anybody out there or in here see an element that can't be factored into irreducibles? After you see it, it's one of those things like staring at those pictures they used to have in the malls in the 80s. We're all scrambled. And, oh, I see the boat. What? Right, this is degree 1. How can that not be factored into irreducible? Because I mean, x in x is irreducible here, right? How can it not be irreducible here? Well, the problem is I can factor things out of x here, but everything that I factor out is an element of the field, and it's therefore a unit. Watch this. Can I factor this? I sure can. X is 2 times x over 2. Notice x over 2 is actually an element of this ring. And so is 2, but 2 is not a unit. Right? This factorization is meaningless here because 2 is a unit in Q, but it is an honest to goodness irreducible element in this ring. So maybe x over 2 is irreducible. Oh no. And it never stops. No matter what you have of degree 1 here, you can pull more stuff out of it. So if you have some big integer m, there is no monomial of degree 1 that is irreducible. No matter what you do, you always can pull more out of it. And the only thing you can pull out of it is degree 0 stuff. So x can never factor into irreducibles. No matter how you try, no matter what you pull out, you're still left over with something that can continue to be factored, which is weird, right? Here is another example that's perhaps more striking. How many of you are kind of fans of number theory? This is the ring of all algebraic integers. And what do I mean by this? Well, this is, for our purposes, the set of all complex numbers, such that this is the set of every complex number that is a root of some monic polynomial. Yeah, how many of you know what I mean by monic polynomial? Monic means leading coefficient. By leading, I mean the highest degree coefficient. So, for example, you have x to the fifth plus 2x cubed plus 4x squared plus 6. This thing, that's a monic polynomial with coefficients in z. If you take, this has got 5 complex roots. If you take those 5 complex roots and throw them in, that's in there. So, the square root of every integer is in there. Every root of unity you could ever come up with is in there. Like I said, any polynomial, any degree, as long as it's monic, coefficients in z, it's in here. What's not clear, perhaps, is the fact that this is a ring, right? Because if I add 2 things that are roots of a monic polynomial, how do I know their sum and product is still a root of a monic polynomial? Well, hear me now and believe me later. It is a ring. It requires a little bit more sophisticated techniques to actually prove this. But this is actually a ring. And in fact, it's an integral domain because it's a subring of complex numbers. This thing is not a field. For example, 1/2 is not in C bar. See if you can show that. Assume that 1/2 is the root of a monic polynomial and get a contradiction from that. Well, actually, I'll do that real quick. Why not do that first? Suppose that 1/2 is a root of a monic polynomial in C, multiplied by 2 to the n. Notice that 2 divides this. So this is even and this is odd. And an odd plus an even is an odd, which is 0 contradiction. Right? So this is not a field. It's got, like, for example, 1/2 is not convertible in here. But every element has a square root. Right? So if alpha is in G bar, and alpha is a root of n plus n minus 1 x n minus 1. Then notice that alpha to the 1/2 is a root of x to the 2n plus n minus 1 x to 2n minus 2 and 1x squared plus n. Notice that this polynomial here, where I just doubled up on the exponents, is also a monic polynomial with coefficients of z. So if alpha is a root to this, notice alpha to the 1/2 is a root of that. And so what that means is in Z, suppose you have an irreducible. Every pi Z factors has and notice neither of these are a unit, because if these are units, then so is pi. So in other words, not only is this ring not atomic, it doesn't have any irreducibles at all. None. Which is kind of weird. But most of the garden variety elements that you're used to, or most of the garden variety rings that you can come up with, at least in the first course, are probably Theorem and therefore atomic. So the atomic domains, there's a lot of them out there, most of them that you will probably ever encounter. Okay, any questions on that? So go home and have interesting nightmares about that. And if there aren't any other questions, I will see you all next time.